Hi students, now we'll talk about section 3.2, which is acceleration vector. As we before talk about the position vector and the velocity vector, now we'll talk about acceleration vector. Starting with the position vector, which is r as a function of t is equal to x of t in I direction, y of t in j direction, z of t in k direction, and we find the velocity vector by deriving take the first derivative with respect to time, and we find vx, vy, vz in I, j, k directions, which is the first derivative of the position vector. The same way we can find, as we know from before, that the acceleration is the first derivative of the velocity and the acceleration is the second derivative of the position. So the first derivative with each component for the velocity, and the second derivative for each component for the position vector will give us the acceleration, and the acceleration will be equal to ax, ay, ez in I, j, k direction. Okay, now it is a simple idea. Let us look at this example. If we have position vector as a function of time, cosine, sine will be used, maybe just a simple function, linear function. So r is equal to 10 cosine pi t in I direction plus 5 sine pi over 2t in j direction plus 10t in z direction. We need to find the acceleration vector and the velocity vector, and then find the position and the velocity and the acceleration at t equal 30. It is easy. Just we need to put 30 in the place of t for these vectors. Okay. The velocity vector is the first derivative of the position vector, and we need to derive each component with respect to time just once. Okay, so the velocity vector will be negative 10 pi sine pi t in I direction plus 5 over 2 cosine pi over 2 t j direction plus 10 k direction. The derivative of cosine is negative sine. The argument inside the cosine is pi t. We need to derive it. It will be pi, the derivative of pi t. This is pi. And we have 10, and this is 10 pi. Negative sine. This is the first derivative of the x component of the position vector in I direction. What about the y direction? The 5 is 5. The derivative of sine pi over 2t is pi over 2 cosine pi over 2t, and 10t, it will be 10 if we derive it. What about the acceleration? It is the same. We need to derive the velocity vector. The derivative of cosine is cosine. We have the argument pi t. We have that derivative of pi t is pi. Then we have pi, another pi from inside, it will be pi squared, and we have 10 and the minus from before. In I direction this. What about the y direction? The derivative of cosine is negative sine. We have negative, new negative sign. 5 pi over 2. We have pi over 2 from inside. For this derivative, it will be here pi squared over 2 squared, which is 4. This is the first derivative of the velocity, of the y component of the velocity in j direction. And the derivative of the constant value, which is 10, is 0. So this is the acceleration vector function in time. Now, what is the value of each of them at t equal 30? We need just to put 30 in place of t for the position, the velocity, and the acceleration vectors. Put t equal 30, 30, 30 each time. This will be equal to, it will be easy. Then we have now, and be careful that the angles and radians, if we need to solve it like in this way, the position at r equal 30, which is equal to 10 I hat, 300 k hat, z 0 j hat, and the velocity is 0 in x direction, negative 5 pi over 2 in j direction, and 10 in k direction, in z direction. And the acceleration just in the x direction, and we have 0 and 0 in y and z direction. So we have the direction of the acceleration just in one direction, in negative x direction, okay? Because we have here x. In radians, we have sine 30 pi is equal to 0. Cosine 30 pi is equal to 1. This is in radian. Cosine 15 pi is in negative 1. Okay? In radians. Look and note that R, V, and A here are not necessarily in the same direction. We have the position vector in I direction and Z direction, in x and z, but the acceleration just in x component, has an x component acceleration. Okay, the velocity, it is not in I and j, it is in j and in I and k, in x and z direction. It is in y and z direction, the velocity. So each one of them has its properties and its direction and its magnitude and length. We can find and look at v, find it from the position, and find the acceleration from velocity using the drawing of vectors. You will use that in the lab section. Be careful for that. If we have two position vectors, r1 and r2, we need to find the velocity. It's easy. We need to find delta r over delta t. Delta r, which is r2 minus r1 over delta t. Okay, what is r2 minus r1? We have just our rows. Okay, as we learned before, r2, this is r2, the same r2, minus r1. We need just to add to r2 negative r1. This is r2, this is negative r1. So this is the vector r2 minus r1, which is this one. Because we have this is r1 and this is r2. The difference between them is r2 minus r1. What is the velocity? It is delta r over delta t. This is delta r. This is the same vector. This is delta r. This one is delta r over delta e. Be careful that the units of delta r is in meters and delta t in seconds. Suppose that delta t is 2 seconds. What is the velocity as a vector? The velocity is the delta r vector over 2. It is the same vector in the same direction, but with a half length. We need to divide over 2. If the time is 3, then we need to divide over 3, and so on. Is that clear? This is the position vector, and this is the velocity vector, and the unit of the velocity, or the velocity, because it is a vector here, is meter over second. What about the acceleration? If we have two vectors, v1 and v2, two velocities, for one body had two velocities, it is accelerated as we see here. What is delta v? Delta v is v2 minus v1. This is v2, this is negative v1. We need to add them together. We have, this is the resultant vector, which is delta v, v2 minus v1, and its units is meters per second, as we know from before. Okay, what is the acceleration? What is the acceleration? The acceleration is delta v over delta t, meter per second over second for units. This is delta v. This is delta v over delta t. Assume that delta t is a third of second, 1 over 3 seconds. Then we have delta v over delta t. If we divide this over 3, over a third, then it will be multiplied by 3. Then the acceleration is 3 times length of the initial change in velocity. It is in the same direction but with different length. Okay, let us apply it in a curvy path. If you see, we have a circle in the yellowish line, and we have a body moving on this surface or this circle. This body has two velocities, v1 and v2, and the magnitude of each velocity is equal to the other. So there is no change in its speed. What is the acceleration? By drawing. Okay, the acceleration is delta v over delta t. What is the direction of it? Okay, this is v2, this is v1. This is minus v1 because they are equal. Look at this point, it gives them an equal length. So this is v2, this is minus v1. What is the resultant delta v between them? This is delta v. If we divide over delta t, it will give us the acceleration direction. It will accelerate toward the center of rotation. Now, for constant speed and there is a change in direction, we have acceleration not equal to 0. What if the speed is raised? Okay, we have, this is v1 and this is v2. It is bigger than v1. That body is accelerated. So what is delta v? This is delta v here. Sorry. This is delta v. This is delta v, but if we divide over the time, it will be the acceleration. In this case also, this is delta v. We will see that. Now, what is the change in velocity? It is v2 minus v1. We need to add minus or negative v1 to v2. This is the resultant vector between them, which is delta v. It is not direct to the center of rotation. It goes in the direction of the bigger velocity, which is v2. Now there is a change in speed and the direction, and v2 is bigger than v1. Then the acceleration or the resultant change in velocity will go in direction of the bigger velocity, which is v2. What if v2 is less than v1? Look at this one, v1, this is v2. What is the change in velocity? Is it v2 minus v1? We need just to add negative v1 to v2. Then this is the change in velocity. It is not directed to the center of rotation. Its direction goes to the direction of the bigger velocity, which is v1 or negative v1, in the negative v1 direction. In this case, we need to understand or to see a new definition for acceleration or components of the acceleration. Look at this part of motion, this part. We know that the center of rotation in this direction, and the body moves on the surface, rotates on the surface of that circle. Okay? Now, in the direction of motion, we need to draw or to assume a coordinate system, which is XY coordinate system. This coordinate system rotates and move on the surface of the motion. The parallel direction is tangential to that curve. The perpendicular direction direct to the center of rotation. Now, for the first case, when v1 is equal to v2, we have just a perpendicular acceleration toward the center of rotation, and the parallel acceleration is 0 in the direction of motion. But in the second case, the acceleration has an angle from the radius of rotation. Then we have a tangential component in the direction of motion, and we have a centripetal acceleration toward the center of rotation. We have two components for this acceleration. And the same way, if we have any change in speed, then we have a tangential component. This tangential component will be in positive direction of motion and in parallel motion, okay, in positive parallel direction to the motion. If the second velocity is bigger than the first one, when the acceleration is positive, and the tangential component will be in the negative direction if we have deceleration, which is the negative acceleration. Be careful for these three cases, and this part of this section is important in the lab section. Thank you.